Welcome to Grandpa's Late Nights. It's good to have you here again, kiddo, wherever you are right now. Whatever corner of the world you've curled up in tonight, I'm glad you found your way to the porch. Go on and settle in. Pull the blanket up a little higher if you need to. Let your shoulders come down away from your ears. There's nowhere you have to be for the next little while, and nothing you have to figure out. Just the sound of an old voice, and a slow story, and the dark being kind for once. And before we get going, let me ask you the same thing I always do, because I do like to wonder about it while I talk. Where in the world are you listening from tonight? What time is it in your corner of the dark? Maybe it's late and the house has gone quiet around you. Maybe it's raining somewhere far off. Maybe there's still a lamp on in the other room that somebody forgot to switch off. I like to picture all of you out there, scattered across the whole turning planet. All of you lying still in your separate beds. All of you listening to the same slow voice. If you feel like it, you can tell me down below where you are. I always read them in the morning with my coffee. And if these late-night ramblings help you drift off, well, a like and a subscribe means an awful lot to a small, sleepy little channel like this one. I'm just an old fellow talking into the quiet, and folks like you are the only reason the porch light stays on. So thank you, truly, to everyone who's already here. It keeps a small creator going more than you know. All right, that's the last of the housekeeping. Let's get to the good part. Now I want you to try something for me. It won't wake you up. If anything, it might do the opposite. I want you to lie there and imagine that a sound is passing through you right now. Not a loud one. Not a sharp one. Nothing that would make you flinch. A note. A single, low, endless note. So low that you have never heard it, and neither has anyone who has ever lived. So low that no ear that has ever existed on this earth could catch even the faintest edge of it. And here's the strange, soft, almost tender part. It is passing through you anyway. Right now. Through the blanket, through your chest, through the pillow under your head. It's washing through the whole room, and through the whole house, and through the ground beneath the house, and through the entire planet you're lying on. And it has been doing this the whole time. Your whole life. Long before your life. It has been humming through the galaxy for very nearly the entire age of the universe. We just never had ears fine enough to notice. That's the thing I want to tell you about tonight. In the year 2023, after 15 long and patient years of watching, a group of astronomers announced that they had finally felt it. A low background hum, a rumble, spread all through the sky. Not a sound in a fireworks sense, not a bang or a chime. Something far stranger and far gentler than that. And the way they caught it is one of the loveliest, most patient, most quietly astonishing things human beings have ever done. They didn't build a giant machine to do it. Not really. What they did instead was borrow dozens of dead stars scattered across thousands of light years and listen to them tick. But I'm getting ahead of myself. We've got all night. There's no rush at all. Let's take it slow, the way we always do, one small piece at a time. And if you drift off somewhere in the middle, that's perfectly all right. The universe will still be humming when you wake up. It's not going anywhere. It's very patient, this note. It's been holding it for billions of years. It can wait for you. So let's start with the most obvious question of all. The kind of question a child would ask, which is usually the best kind. If something is humming, then what on earth is doing the humming, and is it really a sound at all? Let me put your mind at ease on that second part first, because it's important, and because almost everybody gets it wrong. This is not a sound, not in the way you'd normally mean it. When I speak to you, my voice pushes on the air, and the air pushes on the air next to it, and that little shove travels along until it wiggles the tiny bones inside your ear. And your brain reads that wiggle as my voice. That's what a sound is. It's a squeeze traveling through air. And that means a sound needs air to travel through. Out in the great empty dark between the stars, there is no air. There's nothing to squeeze. So, in the ordinary sense, space is silent. Perfectly, completely silent. If a star exploded 100 light years away, you would never hear a thing. So when I tell you the universe is humming a note, I don't mean there's a sound out there rolling through the emptiness. There isn't. What I mean is something a good deal harder to picture, and a good deal more beautiful once you do. The thing that's humming isn't the air, it's space itself. Now I know that sounds like a riddle, so let me sit with it a moment, gently, and try to make it feel real to you. You probably think of space as just, well, nothing. Emptiness, a stage for the stars to stand on. An absence. But space isn't quite an absence. It's more like a fabric, a very fine and very stretchy fabric that everything is embedded in. You're sitting in it right now. This whole room is stitched into it. And that fabric can be stretched, and it can be squeezed, and when something enormous happens far away, a ripple can travel through that fabric, stretching and squeezing space itself as it goes, the way a ripple travels across the top of a still pond after you drop a stone in. That's what a gravitational wave is. A ripple in the fabric of space. When one passes through you, space itself very gently gets a little longer in one direction and a little shorter in the other. You get very slightly taller and very slightly narrower and then very slightly shorter and wider, over and over as the wave rolls by. You'd never feel it. It's far, far too small for that. But it's real and it's happening. And here's where the word note comes back in. Because it fits after all. A sound has a pitch, doesn't it? A high squeaky note or a low rumbly one. And what makes a note high or low is how fast it wiggles. A high note wiggles the air very quickly, hundreds or thousands of times a second. A low note wiggles it slowly. The deepest note you can hear, the lowest rumble your ears can catch, wiggles about 20 times a second. Anything slower than that, and your ears just can't grab hold of it. It slides right past you. Well, these ripples in space wiggle slowly. And I don't mean a little slowly. I mean the kind of slow that stops you in your tracks once you really take it in. A single wiggle of this hum, one full stretch and one full squeeze, one complete up and down, takes years. In some cases, decades. Think about that for just a moment. A note so deep that between one beat and the next, whole years of your life go by. Seasons come and go. Children grow up. And the wave still hasn't finished a single oscillation. Your ears catch 20 wiggles a second at the very slowest. This note takes years for one. So it's not just a bit too low to hear. It's not off the bottom of a piano, it is something like a billion times too low to hear. It is so far below the floor of hearing that the word hearing stops meaning anything at all. Nothing with ears could ever catch it. Not a human, not a whale, not any creature that has ever lived or ever will. That's what the title means when it says a note too low for anyone to have ever heard. It's not a figure of speech, it is the literal, honest truth. This is the deepest note in all of creation, and no ear was ever built that could touch it, and yet it's here, passing through you, right now, in the dark, while you lie still. So then, if no ear can hear it, and it's a stretching of space so faint you'll never feel it, How in the world did anybody ever find it? How do you catch a note that takes years just to hum once? How do you feel a stretch in space so small that it barely moves anything at all? This is where the story gets wonderful. Because the answer is the strangest, most patient, most unlikely instrument human beings have ever used. And to explain it, I have to tell you about dead stars. I want you to picture a star, a big one, much bigger than our sun. It's been burning for millions of years, holding itself up against its own crushing weight by the fire roaring in its core. That fire pushes outward and gravity pulls inward, and for a long, long time the two are balanced, and the star shines. But a star like that lives fast and burns through its fuel, and one day the fire in the middle runs out, and the moment it does, there's nothing left to hold the star up. Gravity has been waiting patiently the whole time, and now it wins. The whole enormous star collapses inward on itself in less than a second, and then it rebounds and blows itself apart in a titanic explosion, a supernova. For a little while, that one dying star can outshine an entire galaxy. But that's not the part I want you to hold on to. What matters for our story tonight is what gets left behind. Because in the very center, while the outer layers are being flung across space, the core of the star gets crushed. And I mean crushed in a way that's almost impossible to imagine. Gravity squeezes the core so hard that the atoms themselves give up. Everything gets packed together tighter and tighter until you're left with a tiny, unbelievably dense ball. Let me try to give you a feel for how dense. Take about 1.5 times the entire mass of our sun, all of it, and crush it down until it fits into a ball only about 20 kilometers across. That's a small city. You could drive across it in 20 minutes, if you could drive across such a thing, without being flattened into a smear one atom thick, which of course you couldn't. A whole sun and a half squeezed into the size of a town. The stuff it's made of is so dense that a single teaspoon of it would weigh something like 1 billion tons. 1 teaspoon, 1 billion tons. More than every car and every building and every person in a great city, all balanced on a single spoon. We call this crushed leftover core a neutron star. And that's really what it is. A star's corpse. The dead, compressed heart of something that used to shine. All across the galaxy, scattered through the dark, there are these little stellar tombstones, the remains of stars that died long ago. They are among the strangest objects in all of nature. And they're about to become our instrument. Because here's the thing about a neutron star. When that great big star collapsed down into this tiny ball, something happened that happens to lots of spinning things when they pull themselves in. Think of an ice skater. When she's spinning with her arms flung out wide, she turns slowly. But when she pulls her arms in tight against her body, she suddenly whirls around much faster. Same skater, same spin, but tucked in tighter, so she turns faster. Well, a giant slowly turning star that collapses down into a tiny ball does exactly the same thing, only to an absurd degree. All that spin gets concentrated into that little 20-kilometer sphere. And so these dead stars can spin. Fast, some of them turn many, many times every single second, and that's still not the strangest part. A neutron star has a powerful magnetic field, and out of its magnetic poles it fires 2 narrow beams of radio waves, streaming out into space like 2 searchlights. Now, the poles usually don't line up with the way the star is spinning. So as the star whirls around, those beams sweep through space in great circles, round and round, exactly the way the beam of a lighthouse sweeps across the sea. And every time one of those beams happens to sweep across the Earth, our radio telescopes catch a little pulse, a blip. And then the beam swings away, and then it comes back around and sweeps us again, and we catch another blip. Round and round, blip after blip, as steady as anything. That's why we call them pulsars, pulsating stars. A dead star, spinning in the dark, flashing a beam past us over and over like a lighthouse at the edge of the world. Now I want to tell you about the discovery of these things, because it's a lovely little story and it belongs to the quiet part of the night. Back in 1967, a young woman named Jocelyn Bell Burnell was a PhD student working with her advisor, Anthony Hewish. And she was going over long rolls of chart paper, the readouts from a radio telescope, mile after mile of squiggly ink lines, looking for anything interesting. And she noticed a little bit of, well, she called it scruff, a funny little bit of regular fuzz that kept showing up in the same patch of sky, and when they looked closer, they found it was a signal pulsing with astonishing regularity. Blip, blip, blip. Perfectly spaced. So perfectly spaced, in fact, that at first nobody could quite believe it was natural. It was so precise, so metronomic, that for a little while, half in jest and half in genuine wonder, they nicknamed that first source LGM-1, Little Green Men, because who else but some distant intelligence could be sending out a signal that regular? It wasn't Little Green Men, of course. It was the first pulsar anyone had ever found, that first dead star sweeping its lighthouse beam past the Earth. They gave it the proper name PSRB 1919+21. And it opened up a whole new corner of astronomy. There's a bittersweet footnote to the story, and I'll give it to you honestly, the way I try to give you everything. When the Nobel Prize was awarded for the discovery in 1974, it went to Anthony Hewish and to another astronomer named Martin Ryle. Jocelyn Bell Burnell, the student who actually spotted the scruff on the paper, was left off the prize. A lot of people thought that wasn't right, and it's remembered to this day. I just think she deserves to have her name said aloud on a quiet night like this one. Jocelyn Bell Burnell. She found the first of the dead stars. Now, most pulsars spin fast, but there's a special breed of them that spins almost unbelievably fast. We call them millisecond pulsars because they complete a whole rotation in just a few thousandths of a second. Try to picture that. This is a dead star, a ball heavier than the sun and the size of a city, and it is spinning hundreds of times every single second. One of them, the first of its kind that we found, is called PSRB 1937+21. It turns 641 times a second, 641 full rotations every second, an object heavier than our sun. If you could somehow stand on its surface and survive, the entire universe would be a smeared blur of light whipping around you faster than you could ever follow. And it just keeps going, and going, and going, out there in the silent dark, and has been for ages beyond counting. There's another one I'll name for you, PSR J4374715, which is the nearest and brightest of these millisecond pulsars and a real workhorse for the astronomers who do this timing. A good, close, reliable dead star. You get fond of them once you learn their names. And here's the property that turns these spinning corpses into the finest scientific instrument ever used. They are steady. Almost beyond belief, they are steady. Because a millisecond pulsar is so massive and spins so fast and has so much momentum wrapped up in it, almost nothing can disturb it. It just keeps ticking, blip after blip, at a rhythm so perfectly regular that it rivals the best atomic clocks that human beings have ever built here on Earth. The very finest atomic clocks in our best laboratories, kept in careful conditions by teams of scientists, are matched by these dead stars sitting out in the freezing dark, doing nothing but spinning. We can predict when the next pulse from one of the good ones will arrive, years in advance, and be right too, within a few tens of nanoseconds. Let me make sure that word lands softly, because it's going to matter a great deal before the night is through. A nanosecond is a billionth of a second. It's such a small slice of time that it's very hard to hold in your head at all. In one single second, there are a billion nanoseconds. The same way there are about that many seconds in 30 years. So when I tell you we can predict the tick of a dead star to within tens of nanoseconds over years and years, I'm telling you we know when its lighthouse beam will sweep past us, out to a sliver of time smaller than you could ever hope to feel. These are the most precise natural clocks in all the universe. And nobody built them. They simply are what a star becomes when it dies, just so. Now, you might wonder how a dying star ends up as such a perfect little clock. And there's a gentle answer to that too. The very fastest and steadiest of these, the millisecond pulsars, weren't always so quick. Many of them are old. They spun down long ago, the way an old top slows and wobbles. But then, something brought them back to life. A lot of these pulsars have a companion, another star orbiting close beside them. And over long ages, the pulsar's fierce gravity pulls a stream of material off that companion, and as that material spirals down and lands on the pulsar, it gives it a push. A little shove of spin, again and again, over millions of years. And that's slow. Patient feeding winds the dead star back up like a child winding a music box, faster and faster, until it's spinning hundreds of times a second again. Astronomers have a lovely word for these. They call them recycled pulsars. Old stars, spun back to life by their neighbours, made new again, made into clocks. So there they are. That's what we've got to work with. Dozens upon dozens of dead stars, scattered across thousands of light years of our galaxy. Each one a spinning corpse the size of a city and heavier than the sun. Each one flashing a radio beam past the Earth, over and over, as steady as the finest clock ever made. Some of them turning hundreds of times a second, all of them ticking away in the dark, keeping better time than anything humanity has ever built, and they've been doing it for longer than there have been people to notice. And this, kiddo, this is the instrument. This is how you catch a note too low for anyone to hear. Not by building some vast machine of steel and glass. Not by launching anything into space, but by finding the clocks that nature had already scattered across the galaxy, learning their rhythms one by one, and then watching, very patiently, for one of those perfect ticks to slip. Because think about what a gravitational wave does. It stretches and squeezes space itself. And if a ripple in space rolls through the stretch of galaxy between one of those dead stars and us, then for a little while the distance the pulse has to travel to reach us gets a tiny bit longer or a tiny bit shorter. Space itself has been stretched along that path. And so the pulse arrives a hair early or a hair late compared to when our flawless prediction said it should. Not by much. Not by anything you could ever notice with a stopwatch, by billionths of a second. But we know these clocks so well, down to those tens of nanoseconds, that a shift that small does not go unseen. It's like knowing a friend's footsteps so well, the exact rhythm of them coming up the walk each evening, that you'd notice if just once they arrived a single heartbeat out of step. You wouldn't know why. But you'd know something had passed between you. That's it. That's the whole secret, in its simplest form. You take the steadiest clocks in the universe, dead stars that keep time to the billionth of a second. And then you wait, and you watch, and you look for the moment when a ripple in space itself nudges their ticks ever so slightly out of place. And when enough of them slip together in just the right pattern, you've felt the hum. You've heard, in a manner of speaking, the note too low for anyone to have ever heard. But oh, there's so much more to it than that. Because it's one thing to say we'll watch for a tick to slip. It's another thing entirely to actually do it across dozens of stars over 15 long years, and to be sure, really sure, that what you found is a wave washing through all of space and not just some ordinary hiccup in one lonely star. There's a reason it took 15 years and not 15 days. There's a reason you need not one dead star, but many. And there's a beautiful, hidden fingerprint that these waves leave behind, a signature that no other thing in the universe can fake, and it's the part of this story that almost nobody ever bothers to explain. We'll get to all of it, slowly, the way we always do. For now, just lie there a while and hold the picture in your mind. Dozens of dead stars, the crushed hearts of suns that died before you were born, spinning silently in the dark all across the galaxy, each one flashing its lighthouse beam toward a small blue world, each one keeping perfect time. And a great slow ripple in the fabric of space, rolling gently through all of them, and through the space between them, and through the little planet in the middle, and through the bed you're lying in, and through you, stretching everything by the smallest amount there is, and then letting it go. Over years. One long, low, patient note, holding steady since almost the beginning of time. You've been sitting inside the instrument your whole life. We all have. We just didn't know how to listen. Rest easy now. The dead stars are still ticking, the note is still humming, soft and low and endless, and it'll keep right on humming while you drift. There's no hurry at all. We'll pick up the thread in just a moment, and I'll show you how they took these scattered clocks and turned them into a single detector as wide as the whole Milky Way. But there's no need to stay awake for it. It'll keep. It's kept for billions of years already. So let your breathing go slow, and even now, let the pulsars spin. Let the space around you stretch and settle as gently as the tide. And I'll keep talking, low and easy, here on the porch in the dark, while the whole quiet universe hums its one deep note beneath everything. Too low for any ear, and somehow, tonight, close enough to feel. So here is how it works. Or rather, here is how you build the largest scientific instrument in the history of our species without building anything at all. Think about what a detector usually is. When you want to measure something tiny, you build something precise. LIGO, the instrument that first caught a gravitational wave directly back in 2015, is a staggering feat of engineering. 2 tunnels, each 4 kilometers long, cut across the desert and the swampland of Louisiana and Washington state, with mirrors polished to within a fraction of an atom's width, isolated from every vibration the Earth can produce. Laser beams folded back and forth inside a near-perfect vacuum. The whole apparatus cost hundreds of millions of dollars and took decades of work by thousands of scientists and engineers, and it is, genuinely, one of the most precise instruments humans have ever constructed. Its arms are 4 kilometers long. 4 kilometers, that's a nice long walk. You could do it in under an hour. On a clear day you could see from one end to the other. Now, the gravitational waves that NANOGrav is looking for, the low background hum we've been talking about, the note the universe has been humming all this time, those waves have a wavelength. Waves always do. The wavelength is the distance from one crest to the next, the physical span of a single ripple. For the wave's LIGO catches, that's not so different from the instrument itself, manageable, terrestrial, the kind of scale engineers can work with. For nanohertz gravitational waves, the wavelength is something else entirely. A wave cycling once every year or so, travelling at the speed of light, which gravitational waves do, exactly, covers light years in a single oscillation. Not kilometres. Not millions of kilometres. Light years, the distance it takes light itself, the fastest thing in the universe, a full year of travelling to cross. We're talking about tens of light years from one wave crest to the next. Trillions of kilometres per ripple. A single swell of space-time so enormous it would stretch from here to the nearest star and keep going twice, 3 times over, before curling back to its starting point. You cannot build a detector to match that. There is no engineering project on any conceivable scale. You could not tunnel through the Earth in the right direction. You could not stretch mirrors to the moon. You could not, with any machine we have ever imagined or could imagine, span the distance a single nanohertz wave takes up. The math is simply not on our side. But here's where it gets strange. You don't have to build anything. Because nature, over billions of years, already scattered the pieces of a perfect detector across the galaxy. You just have to know how to read them. Each pulsar, remember, is a lighthouse. A dead star, a crushed neutron star spinning hundreds of times a second, sending a narrow beam of radio waves sweeping through the dark. Every time that beam sweeps past Earth, our telescopes catch a pulse. One pulse, then another, each one arriving on a schedule so reliable it would make a Swiss watchmaker feel faintly inadequate. The best millisecond pulsars keep time to within tens of nanoseconds over the course of years, not microseconds, not milliseconds, nanoseconds, billionths of a second. Timing that makes our most advanced atomic clocks look casual by comparison. So you have a pulsar, it's 300 light-years away, let's say, or 800, or 1,000, they're scattered all over the place. And every few weeks, your radio telescope picks up its regular pulse, right on schedule, right on time, reliable as a heartbeat that's been beating since long before the Earth existed. Now imagine a gravitational wave passes. The wave is a ripple in space-time itself, not in anything inside space. In space. The medium. The thing that distances are measured through. And as it passes, the distance between you and the pulsar changes. Not because either of you moved, not because anything pushed you. The space between you stretched or squeezed just a little, for a little while. The ruler you would use to measure the gap between you and that pulsar actually got slightly longer or slightly shorter while the wave moved through. And here's the consequence. If the space between you and the pulsar stretches, then the pulsar's radio pulse has a little farther to travel to reach you. It takes a tiny bit longer. It arrives late, not by much, by tens of nanoseconds, or maybe 100 or 2 accumulated over time. Not one pulse arriving late, that could be anything, a hiccup in the interstellar medium, a slight error in your timing model. No, a gradual drift, a slow lean in the arrival times, a pattern that builds over months and years as the wave moves through. And if space squeezes, the pulse arrives a tiny bit early. That is the whole measurement. That's the whole principle. You take a clock you can't move, can't break, can't interfere with. A dead star spinning in the dark, and you watch whether its pulses arrive on exactly the schedule you predicted. If they do, space between you was quiet. If they slip, even by a breath, something passed through. The pulsar is one arm of your detector. The line running from Earth to that star is the arm. A single arm, hundreds or thousands of light years long. The passing wave stretches and squeezes that arm, and you feel it in the tick of the pulsar's beam. Hundreds of light years, thousands in some cases. Compare that to 4 kilometers. LIGO's arms are 4 kilometers long. The arms of a pulsar timing array are hundreds of light years long. That's not a modest improvement. That's not an order of magnitude or two. The difference in scale is almost beyond comparing. It's something like the difference between the width of your thumbnail and the distance to the moon, and then past it. The effective instrument, the combined detector formed by all the pulsars NANOGrav was watching, spans the Milky Way. Not approximately. Not in a poetic sense. The baseline of the measurement, the physical length of the arms, is measured in thousands of light years, which is to say, it is comparable to a significant fraction of the galaxy's own diameter. You built a galaxy-sized detector. Humans did. Working from Earth, using radio telescopes, watching dead stars, without launching a single spacecraft, without leaving the ground. There's a moment where that lands differently the more you sit with it. The instrument didn't require a new material or a revolutionary technology in the traditional sense. It required patience and precision and the recognition that the universe had already done most of the work. The pulsars were already there, already spinning, already ticking. They'd been ticking for millions of years before the first radio telescope was ever built. We just had to show up, point our dishes, and listen carefully enough. Carefully enough, in this case, meaning carefully enough to notice a shift of tens of nanoseconds, over years. Let that sit for a moment. A nanosecond is 1/billionth of a second. Light, in 1 nanosecond, travels about 30 centimeters, roughly the length of your forearm. The timing shifts the scientists are trying to detect are on the order of that. A few dozen arm lengths of light travel time, buried in the ticking of a star hundreds of light years away, accumulated over years of watching. The space between Earth and a pulsar thousands of light years distant might change by something on the order of meters. The wave, for all its unimaginable scale, produces only the tiniest, most delicate nudge, and the timing shifts that result are billionths of a second. No single telescope, no single moment of observation could catch that. It's far too small. The natural variations in how a pulsar's signal travels through the interstellar gas, the small wobbles in Earth's own orbit, the errors in our best models of where every planet in the solar system sits at any given moment, all of these could easily drown out a shift of 100 nanoseconds. Easily, so you don't measure one pulsar, you measure dozens, and you measure them for years, and years. And more years. And the signal you're looking for, the true signature of a gravitational wave background moving through the whole galaxy, should show up not as a shift in one pulsar, but as a correlated pattern across all of them. Not identical shifts, not all drifting the same direction at once, but a specific, mathematically predicted relationship between the shifts in different pulsars depending on where they sit in the sky relative to each other. A fingerprint. But we'll come to that fingerprint in a moment, because it's the most beautiful part of all of this, and it deserves its own time. For now, just settle into the scale of the method. Dozens of dead stars, each one a clock, each one an arm of the instrument, each one patiently broadcasting its pulses toward Earth week after week for 15 years. The scientists at NANOGrav were timing 68 millisecond pulsars, 68 of them, gathering the data from the early 2000s through to 2020. 67 of those 68 had enough data in them, enough accumulated observations over enough years, to enter the final analysis. 67 cosmic clocks, spread across the sky, each one trusted, each one watched, each one measured against the finest predictions human mathematics can produce. And in the accumulated ticking of all 67 of them together, something was there. Something quiet and deep and enormously old, woven through the data like a very faint, very patient signal that had been waiting a very long time to be read. Quick reminder, just for a moment, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. Now, why 15 years? That question has a cleaner answer than you might expect. It isn't about the limitations of the instruments. It isn't about funding or personnel or the pace of academic science, though all of those played their part. The fundamental reason it took 15 years is simpler and stranger. The waves themselves demanded it. The physics set the clock, not impatience, not resources, not anything human beings could have accelerated. Think about what it means that these waves cycle so slowly. A nanohertz gravitational wave has a frequency of roughly 1 oscillation per year or per decade, or somewhere in that range. The very word nanohertz means a billionth of a cycle per second, which translates to a cycle that takes years to complete. From one crest to the next, from stretch to squeeze and back to stretch again, years pass. Out in the universe, among the massive orbiting objects producing these waves, orbital periods span years, decades, sometimes longer. To detect a wave, you need to see it change. You need to catch the rise and the fall of at least one oscillation, ideally several, so you can distinguish a real periodic signal from a one-time glitch or a gradual drift from some mundane instrument problem. With a wave that cycles once every few years, that means you need to watch for at least several years just to see one full cycle. To build up real statistical confidence, to see the signal rise above the noise with any certainty, you need many cycles. And many cycles at this frequency means a very long vigil. There's no shortcut. You cannot compress the observation time without cheating the physics. The wave doesn't care how long you've been watching, it will cycle at its own pace, on its own schedule, according to the orbits of the objects producing it and the speed of light carrying the disturbance outward. You must match your patience to the waves. 15 years, roughly speaking, is the minimum stretch over which the signal had a fighting chance of rising clearly above everything else in the data. It's a little like trying to measure the tide. If you station yourself on the shore and watch for 30 seconds, you'd see water. You might notice it moving slightly, one way or another. But you wouldn't see the tide, the full rise and fall over hours, because you haven't waited long enough. Now imagine tides that rise and fall, not over 6 hours, but over 3 years. You'd need to watch for decades just to see a handful of tidal cycles. That's the position the scientists were in. They didn't choose 15 years as an arbitrary milestone. The physics chose it for them. This is also, incidentally, why no single year of the dataset and no single telescope session could produce the answer. The information wasn't in any one observation, it was spread across all of them, embedded in the long-term trends, in the gradual drifts and correlations that only emerged when years of carefully gathered data were laid on top of each other and examined as a whole. Every few weeks, year after year, the radio telescopes would point at their assigned pulsars, collect the pulses, record the precise arrival times, and add those measurements to the growing archive. Not dramatic, not fast, just patient, methodical work, week after week, adding one more data point to a 15-year-long experiment. There is something almost monastic about it. In an era when science is often expected to move quickly, to produce results and papers and headlines at a rapid pace, this project asked its scientists to do the opposite. To trust the method, tend the archive, keep the telescopes pointing in the right directions, and wait for physics to have its say in its own time. Some of the people who started this work in the early 2000s had done significant parts of their careers by the time the signal became clear. The idea itself, the idea of using pulsars as a gravitational wave detector, is older than many of the scientists who worked on the 2023 result. It goes back to the late 1970s, when gravitational wave physics was still largely theoretical, when the only indirect evidence that gravitational waves existed was coming from a peculiar pair of neutron stars discovered just a few years earlier. In 1978, a Soviet astrophysicist named Mikhail Sazhin published a paper pointing out that a passing gravitational wave would shift the timing of pulsar pulses in a detectable way. The idea was there, clearly stated, mathematically laid out. A year later, in 1979, an American physicist named Stephen Detweiler worked it out more carefully, showing how sensitive such a measurement could be. How the timing residuals, the tiny differences between predicted and observed pulse arrival times, would carry the signature of the wave. Neither Sazhin nor Detweiler had a detector to propose. They had an idea, a beautiful one. But in 1978 and 1979, the millisecond pulsars that would make the idea practical hadn't even been discovered yet. The first millisecond pulsar, PSRB 1937 plus 21, spinning 641 times per second, the kind of precision timekeeper the method required, wasn't found until 1982. And even then, the computational tools and the observational infrastructure to time dozens of pulsars simultaneously across years of data didn't exist. The idea waited, patiently, as ideas in physics sometimes must. In 1990, two astronomers named Roger Foster and Donald Backer formalized the array approach. The idea that you wouldn't just watch one pulsar, but many, spread across the sky and combine their timing data into a single coordinated measurement. One pulsar gives you one noisy signal. Dozens of pulsars give you a correlated dataset where the signal can be separated from the noise by comparing what different pulsars do at the same time. Or rather, what patterns emerge in their collective behavior when something is genuinely washing through the space they all share. Foster and Backer's paper laid the conceptual groundwork for what would eventually become NANOGrav and its partner arrays around the world. 12 years between the first idea and the first blueprint for the actual instrument, and then another 30 years, or thereabouts, from blueprint to result. Sazhin wrote his paper in 1978. The 2023 announcement came 45 years later. Science, at its deepest and most patient, moves on timescales that feel strange to us, to creatures whose lifespans are measured in decades, who experience urgency and impatience and the desire to know now. But the universe sets the pace. The waves cycle when they cycle. The signal builds when it builds. You tend the instrument and you wait. There's something restful in that, if you let yourself feel it. The idea that some things simply cannot be rushed, that you can set the most precise clocks imaginable to work, point the most sensitive radio ears in the world at the sky, write the most careful mathematics you know, and then simply wait. Let the data accumulate. Let the signal build. Trust that the physics is there and will show itself when enough time has passed. 67 pulsars, watched every few weeks for 15 years. Tens of millions of individual pulse arrival time measurements, each one recorded, each one carefully stripped of the known sources of variation. The pulsar's own spin-down, the Earth's motion through the solar system, the wandering of interstellar electrons that can slow a radio signal in unpredictable ways, each one reduced to what's called a timing residual. The small difference between when the pulse actually arrived and when the best available model said it should. And in those residuals, in the long, patient record of how 67 dead stars had been behaving for a decade and a half, the answer was waiting. But a table full of numbers, even a very large and carefully gathered table, isn't by itself proof of anything. Noise can masquerade as signal. Instrument errors can produce patterns. Gaps in the data can create apparent trends. The history of science is full of promising signals that turned out to be artifacts, whispers from the equipment rather than from the sky. So when you have a decade and a half of timing data from dozens of pulsars, and you notice something unusual in it, something that looks, maybe, like a common low-frequency variation across many of them, the obvious question is, how do you know it's real? How do you know it's gravitational waves, and not just noise? Not just some systematic error in how the clocks were calibrated, or some common wobble in the model of the solar system you use to correct for Earth's own motion, or some slow drift in the instruments themselves? That question deserves a careful answer. And it has one. The most elegant one imaginable, in some ways. A mathematical fingerprint so specific to gravitational waves, and so unlike any other source of error, that finding it in the data was the whole ballgame. It's called the Hellings-Downs curve, and the story of how it works and what it means is where the whole 15 years of patience suddenly becomes worth every year of waiting. So hold that question gently for a moment. We've established the instrument, the dead stars, the nanosecond timing, the arms stretching hundreds to thousands of light years, the whole Milky Way pressed into service as a single enormous sensor. We've walked through why 15 years wasn't a choice, but a necessity, why the waves themselves dictated the pace, and how a handful of theorists in the late 1970s and a careful engineering of the method in 1990 laid the track this whole train was eventually going to run on. And now we're standing at the point where data became evidence, where decades of careful, unglamorous, recurring observation were held up against a mathematical prediction made 4 decades earlier, and the two matched. What does a gravitational wave background actually look like in a pulsar timing dataset? Not what does it look like on a screen with colors and animations, what does it look like mathematically, in the only form you can actually test? That's the question Ronald Hellings and George Downs sat down to answer in 1983. And the answer they found is strange and specific and beautiful in exactly the way that something true tends to be. 2 pulsars. That's where you start. You've been watching them both for years. You have their timing residuals, all those small early and late deviations from the predicted pulse schedule. And you want to know, do these two pulsars show correlated behavior? When one pulsar's timing residuals drift one way, does the other one tend to drift the same way at the same time? And by how much? Hellings-Downs worked out precisely what the answer should be if the culprit is a gravitational wave background permeating all of space. And the key, the thing that makes it a fingerprint rather than just noise, is that the correlation between any two pulsars depends on where they are in the sky relative to each other. Two pulsars that sit close together, that you'd see near each other if you looked up, should show a strong positive correlation. Their timing residuals should tend to drift together, early together, late together. Two pulsars 90 degrees apart in the sky, at right angles from each other as seen from Earth, should show something close to zero correlation, maybe a slight negative one. They're being stretched and squeezed by the same wave, but from different angles, so the effects partially cancel. And two pulsars nearly opposite each other in the sky, almost back to back, should show a different kind of correlation again, not the same as the close-together ones, but related in a mathematically specific way. The whole pattern is called a quadrupole correlation. Quadrupole because gravitational waves, by their nature, stretch space in one direction while squeezing it in the perpendicular direction. That's the signature of how they work at a fundamental level, the shape of the disturbance they make. And that quadrupole character leaves an unmistakable stamp on how correlated the behavior of pulsars is as a function of the angle between them. When you plot that correlation against the angular separation, when you put angle on one axis and correlation strength on the other, you get a curve. A specific, smooth, mathematically defined curve that rises and falls in a particular pattern. That curve is the Hellings-Downs curve, and here is why it's a proof and not just a pattern. Almost any other source of correlated noise in pulsar timing data would produce a different shape. If there were a common clock error at Earth, some problem with how all the observations were being time-stamped, it would make all pulsars drift the same direction at the same time, regardless of where they sit in the sky. That's called a monopole pattern. Completely uniform across all pulsars, no angular dependence. It would produce a flat horizontal line on the plot, not the Hellings-Downs curve. If there were systematic errors in the mathematical model of the solar system, mistakes in where the planets were assumed to be, which affect how we correct for Earth's own motion through the data, those errors would produce a dipole pattern. Stronger correlation in one half of the sky, weaker in the other, like a tug from one direction. Different curve entirely. Only gravitational waves produce the quadrupole shape. Only a background of waves in space-time itself, with that specific quadrupole character built into the physics of general relativity, produces the Hellings-Downs curve. Finding that curve in the data is the key that unlocks the whole interpretation. Not just extra noise, not just some unexplained systematic, but that particular shape, that particular angular dependence, that mathematical fingerprint. NANOGrav found it. At a significance of roughly 3 to 4 sigma, what scientists usually describe carefully as strong evidence. Not yet the 5 sigma threshold that earns the word discovery in particle physics. Strong evidence is honest. It means the probability of seeing something this convincing from random noise alone is very small, but not yet at the level that forecloses all reasonable doubt. The collaboration knew this, said so clearly, and published accordingly. 3 to 4 sigma. After 15 years of watching 67 dead stars tick. And the curve was there. Not perfectly, not drawn in clean lines against a white background, but there, in the data, in the angular correlations between pulsars spread across the sky. The quadrupole shape that Hellings-Downs computed on paper in 1983, the shape that only a true gravitational wave background should produce, was showing up in the numbers 40 years later. Something was there. Something old and vast and previously silent, finally heard. But let's stay with that curve a little longer, because there is one more layer to it, one more piece of the detection that is easy to skip over and really shouldn't be, because it's the part that shows just how carefully the scientists were thinking, how rigorously they asked themselves the question that any honest scientist must ask. Could this be something else? Could there be another explanation that fits the same pattern? The answer, it turns out, comes from the structure of the signal itself. And to understand that, you need to think about something called the Earth term and the pulsar term. Stay with me here. It is a simpler idea than it sounds. When a gravitational wave passes through the galaxy, it doesn't arrive everywhere at once. Space-time is enormous. A wave travelling at the speed of light through the Milky Way is in transit for thousands of years at a time. And so when we say a wave is passing, what we really mean is that it is continuously washing through, touching different parts of the galaxy at different moments. Now, when that wave reaches Earth, it nudges the measurement here. It changes the timing of all the pulsar signals we receive because it stretches and squeezes the space between us and those distant spinning corpses. That common nudge, the effect of the wave at our end of each arm, is what the astronomers call the Earth term. And because it is happening here, at the telescope, it is the same for every pulsar. Whatever the wave does to Earth at this moment, it does it simultaneously for all 67 pulsars being watched. The signals from PSR J0437-4715 and every other pulsar in the array all carry the same Earth term imprint at the same instant. But here is the beautiful and subtle part. That same wave was also at each pulsar's location sometime in the past. Years ago, or decades ago, or centuries ago, depending on how far away the pulsar is, that ripple in space-time swept through the site where that tiny spinning star rotates in the dark. And at that moment, the wave was doing something to the space-time near the pulsar too. The pulsar was ticking in slightly stretched space or slightly compressed space while the wave was present. And those pulses, those slightly off-rhythm pulses from that past moment, are only reaching Earth now, because they've been travelling across hundreds or thousands of light-years of space to get here. That is the pulsar term. The imprint left by the wave at the pulsar's location, different for each pulsar. Because each pulsar is a different distance away, and at a different angle to the wave passed through each pulsar's neighbourhood at a different phase. One pulsar might have been riding a crest, another might have been in a trough, another somewhere in between. Each one carries a unique signature of the wave from its own distant corner of the galaxy. So what you actually receive from each pulsar is a blended signal, the Earth term, which is the same for everyone, and the pulsar term, which is unique to that star. And when you compare pairs of pulsars, looking for correlations in their timing residuals, you are looking for the specific pattern that a real gravitational wave background should produce when you add those two terms together. The Hellings-Downs curve predicts what that summed pattern looks like across all possible angles between pairs of pulsars. Not because someone invented a curve and then went looking for it, but because the mathematics of general relativity tells you very precisely what kind of correlation structure a stochastic gravitational wave background must produce. It must be quadrupolar. It must show that specific rise and dip with angle. And finding that shape in the data, using real pulsar pairs at real angular separations, is the signature. That is the proof. Not just that something noisy was happening, not just that the timing residuals were larger than expected, but that the something noisy had the exact angular structure that only a gravitational wave background produces. The Earth term, the pulsar term, the quadrupole correlation, the whole intricate scaffolding of the detection, all of it pointing in one direction. Something was there. And so now comes the question that has probably been sitting quietly in the back of your mind since we began tonight. The curve is the fingerprint. The nanoseconds are the evidence. The pattern is the proof. But we have been so focused on the how of the detection that we have not yet asked the obvious, urgent question. What is actually making this hum? What is so big, so slow, so powerful that it can shake all of space-time at once? What kind of thing has been stirring the fabric of the cosmos continuously for the entire age of the universe? And only now have we built the patience and the instruments to feel it. To answer that, we need to think about the universe's most extreme objects. Not extreme in the quick, dramatic way of a supernova, or even in the brief and violent way of two stellar mass black holes colliding as LIGO heard in 2015. Something slower, something older, something so large that its orbit takes not seconds but years, not years but millions of years, and its gravitational footprint is not a sharp shout, but a long, low, geological groan. We need to talk about pairs of supermassive black holes. Not the ordinary black holes, if anything so strange can be called ordinary, that form when massive stars collapse at the end of their lives. Those are the stellar mass variety, maybe 10 or 30 or 100 times the mass of the Sun, compact and fierce and local. The LIGO black holes were in that range. They are, cosmically speaking, small supermassive black holes are in a different category entirely. They live at the centers of galaxies. Virtually every large galaxy we have looked at appears to harbor one at its heart. Our own Milky Way has one, Sagittarius A, roughly 4 million times the mass of the Sun. That is already a number that the mind can barely hold. 4 million suns squeezed into a region smaller than our solar system. But the supermassive black holes that matter for this story are bigger. Much bigger. The kind that live at the centers of giant galaxies, the ones that have been feeding and growing for billions of years, masses of hundreds of millions, sometimes billions, sometimes tens of billions of times the mass of the Sun. Single objects with the gravitational presence of entire galaxies compacted into a region of space you could fit inside our solar system. And here is what happens when galaxies merge. Galaxies collide. It happens. On cosmological timescales, it is not even rare. Over the billions of years of the universe's history, galaxies have pulled each other together by gravity, fallen into each other, stirred and blended, and settled into new configurations. Our own Milky Way is on a slow-motion collision course with the Andromeda Galaxy. It will take a few billion years, but eventually the two will meet. When two galaxies merge, their supermassive black holes do not simply disappear. Each galaxy brings its black hole to the center of the wreckage. As the galaxies blend together, the two black holes, each carrying billions of solar masses, sink toward each other through the newly merged core. Gravity does what gravity always does. It pulls them together. And so you end up with a binary. Two supermassive black holes orbiting each other, a pair of cosmic giants circling their common center of gravity, like two enormous slow dancing partners in the dark. Their orbital periods are not days or years the way planets orbit stars. The timescales for these objects are immense. A single orbit might take thousands of years, or tens of thousands of years. These are slow, ponderous, monumental revolutions happening on timescales that make geological time feel hasty. But massive things in motion generate gravitational waves. That is the core of it. Einstein's general relativity tells us that accelerating masses stir the fabric of spacetime, sending ripples outward at the speed of light. The more massive the objects and the closer they orbit, the more powerful those waves. And with black holes of millions or billions of solar masses, even a slow, wide orbit radiates gravitational energy in the lowest, longest waves the universe can produce. Those orbits, for the kinds of supermassive black hole pairs we are describing, radiate primarily in the nanohertz band, frequencies of billionths of a cycle per second, one wave crest every few years, one complete cycle every decade or more. Exactly the band that the pulsar timing arrays are sensitive to. That is not a coincidence, the scientists noticed after the fact. It is why the pulsar timing arrays were built. The physics of supermassive black hole binaries, the orbital timescales implied by their masses and separations, pointed directly to the nanohertz frequency range long before any signal was found. The frequency match was a prediction. What NANOGrav and its partner arrays were doing over those 15 years was testing whether the prediction was right. And then consider how many such pairs there must be. The universe is enormous. Galaxy mergers have been happening across cosmic history, across billions of years, across billions of galaxies. Every time two large galaxies fell into each other, another pair of supermassive black holes began their slow dance approach. Not one pair, not 100. An enormous population of them scattered across the observable universe at every distance, every mass, every stage of their inspiral, all of them orbiting, all of them radiating, all of them sending their nanohertz gravitational waves out through the cosmos in every direction. Now imagine all of those waves arriving at once. Not one pair's signal, not two, but all of them, from every corner of the observable universe. Billions of pairs, each at a slightly different frequency, each at a slightly different amplitude, all of them superimposed, all of them overlapping, all of them adding together into a single undifferentiated hum. A gravitational wave background. There is an analogy that the scientists themselves sometimes reach for, and it is a good one. Imagine you are outside a football stadium before a big match. From a distance, before you can hear individual voices, before you can make out words or chants or particular shouts, you hear the crowd. A roar. A single, blended, overlapping sound from thousands of people, all doing different things, all at slightly different pitches and rhythms and volumes. Nobody in particular. Just the crowd, as a collective presence. That is the gravitational wave background. Not a single pair of black holes. Not a resolved source that you could point to and say, there, those two, that is what I am detecting. A stadium crowd of supermassive black hole binaries, each one contributing its own low gravitational note, all of them blending into a single undifferentiated rumble. A stochastic background, the scientists call it. A signal with statistical properties rather than a distinct source. Like the crowd roar, it has a character, a spectrum, an amplitude, but you cannot hear any individual voice. Yet, because the spectrum does carry information, not about individual pairs, but about the population as a whole. How many pairs are there? What masses do they tend to have? How tightly are they orbiting? These questions are encoded in the shape of the background signal, in how its strength varies with frequency, in what the scientists call the spectral slope. The measured characteristic strain of the background, a way of quantifying its amplitude at a given frequency, came out at roughly 2 × 10 to the -15th at a reference frequency of 1 cycle per year. A tiny number, written out. 2 followed by 15 zeros below the decimal point. And yet detectable. Detectable after 15 years with 67 dead stars. The spectral slope, the way the signal's strength changes across the frequency range the array is sensitive to, is broadly consistent with what you would expect from a population of supermassive black hole binaries spiraling together under general relativity. The mathematics of how binary systems lose energy and in spiral predicts a specific relationship between frequency and amplitude. And the measured background has something close to that shape. Something close to. Not exact. There is mild tension, a slight difference between the simplest prediction and the measured spectrum. Just enough that physicists are watching it carefully. Just enough to leave open the question of whether there might be something else in the hum as well. Something that we will come back to later. But for now, the leading interpretation is clear. What is humming is a vast population of supermassive black hole pairs. Giants in the hearts of merged galaxies, spread across billions of light years of cosmic history, all of them orbiting, all of them stirring space-time, all of them contributing to the rumble that has been washing through your room, your body, this planet, this galaxy, for the entire age of the cosmos. And to give you some sense of the scale of the objects we are talking about, it helps to have anchors, real ones, objects we have actually measured or at least estimated with some confidence. In 2019, something remarkable happened. The Event Horizon Telescope, a planet-spanning array of radio observatories linked together to act as one enormous instrument, produced the first actual image of a black hole's shadow. The black hole at the center of the galaxy M87, known as M87 star. What they found at the heart of that galaxy, about 53 million light-years away, was a black hole with a mass of approximately 6.5 billion times the mass of the Sun. 6.5 billion solar masses. In a single object. A region of space where gravity is so overwhelming that not even light escapes, with the mass of 6.5 billion stars compressed into a sphere smaller than our solar system. M87 star is not even among the largest known. It sits at the upper end of what astronomers typically call supermassive, edging into a category sometimes called ultramassive. The objects at the extreme end have estimated masses that stretch the imagination even further. TON 618 is a quasar. A quasar is an active galactic nucleus, the intensely bright core of a distant galaxy, where the central black hole is actively swallowing matter, radiating energy in the process with a brilliance that can outshine the rest of the galaxy combined. TON 618 is one of the brightest and most massive quasars known, located roughly 10 billion light-years away. Meaning, we see it as it was when the universe was much younger. Its central black hole has an estimated mass of somewhere in the range of 40 to 66 billion solar masses. A single object between 40 and 66 billion times the mass of our Sun. These are the anchors. These are the kinds of objects that, when they exist in pairs in the merged cores of giant galaxies, and when they slowly orbit each other over thousands or millions of years, generate the signal that 67 pulsars scattered across the Milky Way spent 15 years quietly recording. The low, nanohertz gravitational hum of the most massive pairs in the universe, blended into a background that has been humming through everything since before our solar system existed. It is worth sitting with that for a moment. There is no rush. You are lying somewhere warm right now, maybe in a bed with the covers pulled up, or on a couch with the lamp still on in the corner. And right now, this very moment, without your noticing it, without any instrument in the world being quite sensitive enough to tell you exactly which wave is passing right now at this instant, the space-time around you is being very gently, very slowly, very imperceptibly stretched and squeezed by the combined gravitational influence of every supermassive black hole pair in the observable universe. Every merged galactic core, every pair of cosmic giants slow dancing toward their eventual merger, is contributing a tiny whisper to the hum that surrounds you. It has always been there. Since before the Earth formed, since before the sun ignited, since before the first stars lit up in the early universe, some of the more exotic possibilities suggest, even longer. It was humming through the interstellar gas that would eventually collapse to form our solar system. It was humming through the ancient seas where life first stirred. It has been humming through every living thing, every mountain, every ocean, every quiet bedroom, on every ordinary night. For billions of years. We simply didn't know. Or rather, we knew it should be there. The physics predicted it. Supermassive black holes exist, galaxy mergers happen. The mathematics of general relativity was clear about what the consequence should be. But knowing something should be there and having evidence that it is there are not the same thing. That gap between the prediction and the proof is what those 15 years of patient watching were closing. Think about what the scientists were actually doing during those years. Not building a new telescope, not launching a new spacecraft, not constructing a new detector in a laboratory or a tunnel or a mine. They were watching. Week after week, month after month, year after year, aiming the great dishes of Arecibo and Green Bank and Parkes and the others at the same stars. 67 dead stars, spinning in the dark, ticking with almost mechanical precision, sending their radio pulses toward Earth at the speed of light. Every few weeks, for each pulsar, an observation. The telescope collects the incoming pulses, averages them carefully to reduce noise, determines the exact moment of arrival of each one. Then compares that arrival time to the flawless mathematical prediction, given everything we know about this pulsar's rotation, its position, its proper motion through space. The gravitational influence of the solar system on the light path, the delay caused by interstellar plasma. What exact moment should that pulse have arrived? And then, is there a residual? A tiny difference between predicted and observed, a handful of nanoseconds one way or the other, accumulated not in a single observation but across months and years of watching, as the background signal slowly impresses itself on the timing data. That is the vigil, patient, unglamorous, requiring no dramatic moment of inspiration, but rather the quiet discipline of doing the same careful thing. Correctly, for 15 years without stopping. The pulsars do not know they are being watched. They spin on regardless. Serdar J04374715, the nearest and brightest millisecond pulsar, traces through its rotation hundreds of times a second, sending its radio beam sweeping past Earth like a lighthouse it does not know exists. Pulsar B 1937+21, the first millisecond pulsar ever found, discovered in 1982, spinning at 641 revolutions per second, has been doing so since long before anyone thought to listen carefully enough to use it as a clock. These stars do not care about the experiment. They simply are, ancient and indifferent, doing what gravity and physics and the aftermath of supernova collapses set them to do, billions of years ago. And yet they were exactly what was needed. Nature had scattered them across the galaxy like a gift the physicists only needed the wisdom to unwrap. Dead stars, each one a natural atomic clock, each one broadcasting its ticks into the void, each one available to serve as an arm of a detector that no human hand could ever have constructed. The instrument was already there, already operating, already ticking. You just had to listen, carefully, for a very long time. Now the hum that has been washing through all of this, the signal that 15 years of listening was trying to hear, is not concentrated in one direction. It is not a beam or a ray or a focused thing. It is genuinely a background. It comes from everywhere at once, from every direction, from every galaxy at every distance that has ever hosted a pair of supermassive black holes spiraling together. Which means from essentially everywhere you could point a telescope. That is part of what makes the Hellings-Downs curve so essential as proof. Because if the signal came from one specific direction, one particular source, it would show up differently. Pulsars in that direction would be affected differently from pulsars at right angles to it. The angular pattern would have a preferred axis. But a true gravitational wave background, a genuinely isotropic background that comes equally from all directions, produces the quadrupole pattern that Hellings-Downs calculated. No preferred axis, just that specific, physics-dictated correlation as a function of angle. The fact that the data shows the Hellings-Downs shape, rather than a dipole, rather than a monopole, rather than some asymmetric pointing toward one part of the sky, is what tells you the signal is a true background. Everywhere at once, washing through the galaxy from every corner of the observable universe simultaneously. The crowd roar, not a single voice. Now you may be wondering about the individual voices. If there are billions of supermassive black hole pairs out there, each one radiating its own gravitational wave, couldn't you eventually pull individual pairs out of the noise? Resolve specific sources the way you might, with a very good audio system and very good noise cancellation. Begin to make out individual conversations in a crowded room? Yes, in principle. And that is part of what the future looks like for this field. As the timing arrays continue to run, as more pulsars are added, as the data gets richer and the sensitivity improves. There are what the scientists call continuous wave sources, individual supermassive black hole binaries emitting a steady, resolvable signal rather than blending into the background. The nearest or most massive or most perfectly oriented pairs might be bright enough eventually to be picked out. Not yet, but eventually. The coming square-kilometre array, the SCAR, which when complete will link radio dishes across South Africa and Australia into an instrument of unprecedented sensitivity, is expected to find many more millisecond pulsars, time them with greater precision, and potentially begin to resolve individual sources out of the hum. The crowd roar over time might begin to yield distinct voices. But that is future work. What the 2023 results gave us is the roar itself, confirmed, the background, the whole undifferentiated rumble, shown to have the right signature. The right amplitude, the right general spectral shape, after 15 years of watching 67 dead stars tick. And the amplitude itself tells you something. that measured characteristic strain, 2 times 10 to the negative 15 at 1 cycle per year. A number that sounds abstract until you try to picture what it means in physical terms. That number represents how much space-time is being stretched and squeezed, expressed as a fraction of a distance. At that amplitude, a wave passing through a baseline of thousands of light-years is shifting things by only a few meters. A few meters across thousands of light-years, a tiny wobble proportionally, but the baseline is so enormous that even a tiny wobble becomes, in absolute terms, a measurable displacement. And even that is only detectable because the dead stars at the far end of those baselines are so extraordinarily stable, because millisecond pulsars tick with the regularity of the finest clocks in existence, because the whole extraordinary accident of nature that produces these recycled pulsars, these spun-up stellar corpses with their astonishing rotational stability, happens to produce exactly the right kind of clock in exactly the right place to serve as the far end of a gravitational wave detector. The instrument was the galaxy. The clocks were dead stars. The patience was 15 years. The signal was the hum of a billion pairs of cosmic giants, the slow dance background music of a universe full of merging galaxies. A note so low that a single cycle takes years or decades to complete, far below anything with ears has ever registered or ever could. Far below the lowest note a pipe organ can produce. Far below the lowest note a whale can hear. Far below the lowest note any physical medium capable of carrying sound could transmit to any biology capable of receiving it. Not because it is quiet, but because frequency and hearing have nothing to do with each other here. These are not pressure waves in air. Space-time is not air. The analogy of a note is a frequency analogy, a way of mapping something genuinely alien onto something familiar, and it works, and it is honest, as long as you remember that the thing being stretched and squeezed is not your eardrum, but the geometry of space itself. That is the thing. That is the part that is hardest to hold in mind, and the most important to try. When you lie very still and breathe slowly and feel the ordinary solidity of whatever is beneath you right now, the mattress or the cushion or the floor, you are resting inside something that is not as fixed as it feels. Space is not a rigid container. Time is not a steady clock. They are both part of a dynamic structure, the thing Einstein described in general relativity. A structure that has curvature, that responds to mass and energy, that can carry waves. And those waves are washing through it right now. Through the walls. Through the floor. Through you. The scale of the sources, billions of solar masses in single objects, orbiting each other over thousands of years, scattered across billions of light-years of space. All of them stirring space-time simultaneously, all of their waves arriving here at once, from every direction. The scale of the detection, 67 dead stars timed to billionths of a second, a detector the size of the Milky Way, 15 years of patient watching. And between those two scales, the almost absurd mismatch that is the central wonder of this whole story, the biggest things in the universe, detected by their effect on the tiniest measurable quantity we have. Billions of solar masses. Nanoseconds, that mismatch, that extraordinary gap between source and signal, is perhaps the single most astonishing thing about what happened on the 28th and 29th of June 2023, when the results were finally ready to share with the world. But before we get to that announcement, before we sit with what it meant and what it did not yet mean, there is one more thing to understand about the source. One more layer to the story of the supermassive black hole pairs that makes this detection more than just a confirmation of what was expected. Something that makes it, quietly, evidence in a long-running theoretical argument that has puzzled astrophysicists for decades. Because the pairs exist. That much seems now to be established, at least at the population level. The hum is there. Its spectrum is broadly right for a population of supermassive black hole binaries. The Hellings-Downs curve confirms the gravitational wave nature of the signal. But for a long time, there was a serious theoretical problem with the idea that supermassive black holes in merging galaxies ever actually complete their inspiral and get close enough to radiate significantly in the nanohertz band. A problem with a straightforward name that captures the difficulty neatly. The final parsec problem. A parsec is a unit of distance used by astronomers. About 3¼ light years. 3¼ times the distance that light travels in a full year. On a cosmic scale, not very far at all. And yet, getting two supermassive black holes that are initially separated by large distances down to a separation of roughly 1 parsec is reasonably well understood. The gravity of their host galaxies, the friction of all the gas and stars they move through as they sink toward each other, the dynamical processes in the newly merged galactic core, all of these can carry them efficiently from large separations down to about 1 parsec. And then they seem to stall. The process that was doing most of the work at larger separations. A process called dynamical friction. The gravitational drag that a massive object feels as it moves through a sea of lighter bodies and flings them away becomes less efficient as the two black holes get very close. There are only so many stars and so much gas in exactly the right place to keep feeding energy out of the orbit. Theory suggested that two supermassive black holes might reach about 1 parsec of separation and then find it very hard to get any closer. They might simply orbit there, neither merging nor separating, frozen just short of the threshold. But the nanohertz gravitational wave background is real. Or at least there is strong evidence that it is. And to produce that background, the pairs need to be closer than a parsec. Close enough that their orbital periods are in the years to decades range that radiates in the nanohertz band. Close enough that the gravitational wave emission itself begins to carry energy out of the orbit and drive the inspiral further. Which means that in reality, somehow, something carries them through the stall. Something bridges the final parsec, gas dynamics perhaps, a disk of gas that forms around the binary and exerts torques that tighten the orbit. Or the interaction of the binary with a third body, another black hole or a wandering massive star that kicks energy out of the system. Or simply that the real galactic environments are richer and more chaotic than the simplified models assumed, and the friction remains efficient longer than theory suggested. The detection does not solve the final parsec problem. It does not tell us exactly which mechanism does the bridging. But it quietly implies that something does. If these pairs didn't make it through, the background wouldn't be there. The hum is, in this sense, indirect evidence that nature finds a way. That pairs do tighten, do reach the close radiating regime, do contribute to the background. After 40 years of theoretical uncertainty, that is not a trivial thing to know. So now we reach the moment itself. The morning of June 28, 2023, the NANOGrav collaboration, the North American Nanohertz Observatory for Gravitational Waves, published a set of papers in the Astrophysical Journal Letters. 15 years of data. 68 millisecond pulsars monitored, 67 of them contributing enough timing information to enter the analysis. And in all of that accumulated patience, all those billions of pulse arrivals recorded and logged and compared, there it was. The signal, the correlated shifts, the curve. That same week, not by coincidence, but by careful coordination, 3 other pulsar timing arrays released compatible results. The European Pulsar Timing Array, EPTA, working alongside the Indian Pulsar Timing Array, InPTA, the Parkes Pulsar Timing Array, PPTA, from Australia. And the Chinese Pulsar Timing Array, CPTA, 4 independent collaborations on 4 different continents, watching different pulsars with different telescopes, running different analysis pipelines, and all 4 found the same thing. The same excess in the timing residuals, the same hint of correlation between pulsars that were close together in the sky. The way science is supposed to work when it is working well. Now, here is where I want to be honest with you, because this is important. The significance of the NANOGrav detection came in at roughly 3 to 4 sigma. Around 3.5 sigma is the number you will see most often quoted. And if you have drifted gently through any physics content before, you may have heard that the gold standard for a confirmed discovery in physics is 5 sigma. 5 standard deviations above the noise floor. That is the threshold community agreed on, born from hard lessons, results that looked real at 3 sigma and then evaporated as more data came in. 3.5 sigma is not 5 sigma. So this is strong evidence. The collaboration described it precisely that way, not as a confirmed detection, not as a discovery with a capital D, but as strong evidence for the gravitational wave background. And that honesty is part of what makes it credible. They had every incentive to call it more. The press attention, the headlines, the legacy. But they said, we see it. It is consistent. The fingerprint is there, and we are confident enough to publish. But more years of data will sharpen this, and we want to be truthful about where we stand. That restraint is a kind of scientific courage, actually. It would have been easy to oversell. And the reason more years will help is not complicated. The longer you watch the pulsars, the more oscillations of the wave you accumulate. You are measuring something that cycles once in years to decades, remember. Every additional year of timing adds new signal, narrows the uncertainty, brings the numbers into sharper focus. The experiment does not end with the announcement. It continues quietly every few weeks as radio telescopes around the world point at their assigned pulsars and measure another set of pulse arrivals to the nanosecond. Speaking of those telescopes, let's talk about what it actually took, physically, to run this thing. Because behind all the elegant mathematics of the Hellings-Downs curve and the nanohertz spectrum, there were real instruments. Real dishes pointed at real patches of sky, in real weather, maintained by real people over a decade and a half. For NANOGrav, the 2 most important instruments were the Arecibo Observatory in Puerto Rico and the Green Bank Telescope in West Virginia. The Very Large Array in New Mexico also contributed. Arecibo you may have heard of, that enormous, bowl-shaped radio telescope built into a natural sinkhole in the Puerto Rican hills, 1,000 feet across. The largest single-dish radio telescope in the world for most of its life. It had watched the sky since 1963. It was the kind of instrument that felt permanent, monumental, like a piece of infrastructure that would simply always be there. It was not always there. On December 1st, 2020, with the 15-year dataset still being built, Arecibo collapsed. The supporting cables had been failing over the preceding months. Engineers had assessed the damage, understood that repair was no longer feasible, and announced a controlled decommissioning. But before that decommissioning could happen, the remaining cables gave way on their own in the early morning, and the enormous receiver platform, weighing 900 tons, fell into the dish below. One of the largest, most scientifically productive radio telescopes ever built, gone in seconds. For a project that had relied on Arecibo's sensitivity for years, for a data set that had been accumulating slowly and patiently toward a threshold, this was a real blow. Not a fatal one. The dataset continued with the Green Bank telescope and the Very Large Array, and the international partners with their own instruments carried on as well. But it was a loss, the kind of loss that is felt. Arecibo had timed pulsars for NANOGrav since the beginning of the project, and the data it contributed is woven into those 15 years in a way that cannot be replaced, only inherited and continued with other eyes. Around the world, the partner arrays were watching with their own instruments, Parkes, the iconic dish in New South Wales that Australians call simply the dish, a 64-metre telescope that has contributed to pulsar timing since before the concept of a timing array even existed. The FAST telescope in China, the 500-metre aperture spherical radio telescope, which surpassed Arecibo as the world's largest single dish when it came online, nestled in a natural basin in Guizhou province. Meerkat in South Africa, an array of 64 dishes spread across the Karoo Desert, contributing data to the EPTA effort. The Effelsberg telescope in Germany, the Lovell telescope in England, the Nane telescope in France. A dozen countries, multiple continents, decades of accumulated effort, all aimed at dead stars hundreds of light years away, all trying to catch the universe flinching. And now, quietly, persistently, with the weight of all that combined attention, the universe flinched. But let's sit with one more layer of this, because the source of the hum is probably what you arrived here most curious about. We have talked about what supermassive black hole binaries are, and why they radiate in the nanohertz band, and how their overlapping signals might sum into an unresolved background roar. The measured spectrum, the shape of the signal across different frequencies, is broadly consistent with what a population of supermassive black hole binaries would produce. That is reassuring. It fits. But here is the honest thing, the fit is not perfect. The measured spectrum shows mild tension with the simplest prediction of what a binary population should look like. The slope is not quite what the most straightforward model would expect. And that tension is interesting, because it leaves the door open to something else, or something more. Among the other candidates that physicists actively consider, and none of which are confirmed, there are things that sound almost mythological. Cosmic strings, hypothetical topological defects in the fabric of space-time itself, one-dimensional objects potentially left over from the very early universe, stretched to cosmic scales. If they exist, they writhe and oscillate and radiate gravitational waves across a broad spectrum that would overlap with the nanohertz band. Or primordial gravitational waves from cosmic inflation, the moment, fractions of a second after the Big Bang, when the universe expanded at an incomprehensible rate, and that expansion itself might have produced a gravitational wave background imprinted on the cosmos ever since. Or phase transitions in the early universe. Moments when the fundamental fields of nature shifted from one state to another, the way water shifts from liquid to ice, but at energies and temperatures beyond anything we can replicate in any laboratory on Earth. None of these are the most likely explanation for what NANOGrav found. The supermassive black hole binaries remain the leading candidate by a wide margin on theoretical grounds, but the data cannot rule the exotic sources out yet. And this is extraordinary to think about. The hum washing through the galaxy might carry, mixed into its spectrum, a whisper of the universe's very first instance. A signal born before any stars existed, before any galaxies, before any pulsars to detect it. A memory encoded in the geometry of space-time from a time we cannot otherwise observe with any instrument we possess. More data will help sort this out. More years of timing, more pulsars, finer measurements of the spectral shape. The signal may become cleaner and more clearly point to binaries, or it may show features that no binary population can explain. And then the chase gets genuinely strange. For now, it is an open loop, a beautiful one. And not knowing is not a failure, it is the correct current state of knowledge, held honestly. Let me place this where it belongs in the larger story, because the 2023 result is not a beginning. It is a milestone in a line of understanding that stretches back over a century. And following that line backward for a moment gives the result its proper weight. In 1916, Albert Einstein worked out the mathematical consequences of his general theory of relativity, a theory published just the year before, and found something unsettling even to him. The theory predicted that matter moving through space-time would radiate energy in the form of gravitational waves, ripples in the curvature itself, propagating outward at the speed of light. Einstein did the calculation, and then he worried about it. For the next 30 years, at various times, he doubted that the waves were physically real, or that anything in the universe could produce them at a detectable amplitude. The sources would have to be extraordinarily massive and moving extraordinarily fast. Even then, the waves would be so faint by the time they reached any detector that he could not see how measurement would ever be possible. He was wrong about that last part, slowly, and then all at once, he was wrong. The first hint came not from any detector, but from a pair of dead stars. In 1974, Russell Hulse and Joseph Taylor, working at Arecibo, discovered a binary pulsar, two neutron stars in a tight orbit around each other, one of them a pulsar whose ticks could be timed with great precision. The system is designated PSRB 1930+16. And when they measured the orbital period over years, they found it was shrinking. Slowly, relentlessly, precisely, the two stars were spiraling toward each other, and the rate of in-spiral matched, with extraordinary accuracy, the prediction from general relativity for the energy lost to gravitational radiation. Not the waves themselves, but the footprint of the waves, the orbital shrinkage that the waves left behind as they carried energy away. It was indirect, but it was airtight, and it earned Hulse and Taylor the Nobel Prize in Physics in 1993. Gravitational waves were real. The universe was radiating them. We just had not yet felt any arrive. But go back further still, to where pulsars themselves came from. Because without pulsars, none of this, not the indirect proof, not the pulsar timing array, not the nanohertz background, any of it exists. In 1967, a young PhD student named Jocelyn Bell Burnell, working under Anthony Hewish at Cambridge, was analysing chart recorder paper scrolling out of a radio telescope she had helped build, and she noticed something, a regular rhythmic pattern of radio pulses arriving every 1.3373 seconds like clockwork. Too regular, unnervingly regular. So regular that for a brief, genuinely uncertain period, the researchers half-jokingly labelled the source LGM1, Little Green Men. Because the first hypothesis you try to rule out when you find something that precise and that regular arriving from space is that it is artificial, that someone made it. It was not artificial, it was a neutron star, rotating and beaming radio waves like a lighthouse. The first pulsar ever identified, PSRB 1919+21. And the realization of what it was opened a new branch of astrophysics almost overnight. Suddenly, nature had been found to produce the most precise natural clocks in existence, scattered across the galaxy, spinning and ticking at intervals measurable to extraordinary precision. The instruments for pulsar timing were not built. They were discovered. Nature had already made them. The 1974 Nobel Prize went to Anthony Hewish and to Martin Ryle, who had developed the techniques of radio astronomy more broadly. It did not go to Jocelyn Bell Burnell, who spotted the first pulsar, analyzed the data, and pushed through the initial confusion to characterize what she had found. The omission has been widely discussed and documented in the years since. Bell Burnell herself has handled the question with more grace than most of us would manage. She has gone on to an extraordinary career, and in 2018 was awarded the Special Breakthrough Prize in Fundamental Physics, which came with a $3 million prize she donated entirely to fund scholarships for underrepresented students. The history is complicated. The science she helped initiate is not. And then, after decades of theoretical refinement and engineering ambition and patient construction, came September 14, 2015, the LIGO detector, 2 facilities, one in Livingston, Louisiana, and one in Hanford, Washington, each with laser arms 4 kilometers long, registered a signal. 2 black holes of roughly 30 solar masses each, spiraling together and merging in a fraction of a second. More than 1 billion light-years away. The signal swept through the detector in under half a second, rising in frequency as the black holes accelerated into their final plunge. The peak frequency was around 150 Sh in the audible range. And when researchers converted the signal to actual sound, to pressure waves in air, you could hear it. A chirp. A brief rising tone, lasting less than a second, and then silence. LIGO announced the detection in February 2016. The Nobel Prize followed in 2017. Gravitational waves were no longer theoretical, no longer indirect. They were measured, felt. The universe had spoken directly into an instrument, and the instrument had answered. But here is the thing about that chirp. It was a transient. A single event, arriving and departing in milliseconds, 2 specific black holes merging at one moment in cosmic time, sending out one burst of waves that passed through Earth on one particular Tuesday morning. LIGO is built for exactly this kind of signal, short, sharp, high frequency, sweeping up through the 10 to 1000 Hertz range that its 4-kilometer arms can sense. What the pulsar timing arrays found is something completely different. Not a transient, not a burst, not a single event, a background. Permanent, unresolved, everywhere, a signal that has been present for essentially the age of the universe and will continue to be present for the age of the universe to come. Not a chirp you could play on a speaker, but a vibration so slow that one oscillation spans years. If you tried to translate the nanohertz background into an audible pitch, which you cannot do directly because the mapping breaks down across 20 orders of magnitude of frequency, the pitch would be somewhere around 10 to 20 octaves below the lowest note a human ear can register, below the rumble of a subwoofer, below the infrasound of a volcanic eruption, below the resonant frequency of any natural cavity on Earth. so far below the floor of hearing that the analogy requires a moment to settle. This is not the same band as LIGO. It is not an extension of LIGO into lower frequencies. It is a fundamentally different regime, requiring a fundamentally different kind of detector, measuring a fundamentally different kind of source. Where LIGO hears the final screaming second of two stellar mass black holes merging, the pulsar timing array feels the slow, decades-long breathing of two black holes, billions of times more massive, still in the long middle of their inspiral, still hundreds of thousands of years from their merger. Different instruments, different sources, different epochs of the gravitational wave universe. The spectrum of gravitational waves spans many decades of frequency, and we have only opened 2 windows into it so far. Each one shows a different landscape. The future will open more windows. The Square Kilometre Array, SCAR, is an international radio telescope under construction with sites in South Africa and Australia. When complete, it will be orders of magnitude more sensitive than anything currently in operation. And one of its primary scientific goals is pulsar timing. With the SCAR, researchers expect to monitor thousands of millisecond pulsars compared to the dozens in current arrays. The increased number of clocks, the increased sensitivity, the increased timing precision, all of it translates directly into sensitivity to gravitational waves at nanohertz frequencies. Where the current arrays see a background roar, the SCAR may begin to resolve individual voices within it. Individual supermassive black hole binaries, close enough or massive enough to be distinguished from the hum. Continuous wave sources, steady and locatable, pointing back to specific galaxies where we could then look with optical telescopes and say, there, that merged galaxy. Those 2 cores, those 2 black holes, spiraling slowly toward their eventual union. Every additional year of timing with the existing arrays also helps. Each year is another oscillation of the wave accumulated, another reduction in the uncertainty, another row added to the dataset. The experiment is not over. It is ongoing, quietly, every few weeks, around the planet. And there is another possibility hiding in the data that the future may clarify. If the spectrum of the background deviates enough from what supermassive black hole binaries would predict, if the tension in the slope becomes clearer and sharper with more data, then the case for an exotic early universe contribution grows. Cosmic strings, if they exist, have a characteristic gravitational wave signature. Inflation's imprint would have its own spectral shape. Distinguishing these from each other and from the binary background requires not just more data, but more pulsars and more years and more precision. The SCAR provides all 3. We may, in the coming decades, be able to read from the shape of the nanohertz background a record of events that happened in the universe's first second, before any particle we know of had settled into its current form. A message in the geometry of spacetime, encoded at the beginning and decoded only now, by dead stars serving as the ears. Now, let's come back to something, because I want you to feel the full weight of what was done here before we rest. The stretching and squeezing of spacetime caused by the gravitational wave background changes distances across the galaxy by meters, shifts the effective distance from Earth to a pulsar hundreds of light-years away by an amount you could measure with a tape measure, if you had a very long one, against a baseline of light-years, against pulse arrival times measured in tens of nanoseconds, that is the fractional precision required, apart in some incomprehensible number. And it was achieved not with a single instrument, but with a fleet of dead stars. each one acting as one arm of a detector with no walls, no building, no structure except the galaxy itself. The instrument is the Milky Way. We did not construct it. We could not. No engineering capability we possess could build a detector with arms hundreds of light years long, but nature constructed it over billions of years in the cores of massive dying stars. And the scientists who developed pulsar timing looked at those stars and realized, slowly, over decades, through the papers of Sajin and Detweiler in the late 1970s, through the formal array proposal of Foster and Backer in 1990, through the grinding establishment of NANOGrav and EPTA and PPTA and CPTA and all the rest, they realized that the instrument already existed. It just needed to be recognized. And then used, patiently, for 15 years. Here is the thing I keep coming back to, and I think it might stay with you too. You were inside the instrument the whole time. Not metaphorically. The hum is real. The gravitational wave background is passing through this room, through the bed you are lying on, if you are in a bed, through the wall, through the planet beneath you. A ripple in the geometry of space, cycling once every few years, so gentle that it moves objects by meters across thousands of light years, which sounds large until you realize the scale, but washing through everything, continuously, permanently, as it has been washing through the galaxy since long before Earth formed, since long before the Sun ignited. Since the first galaxies formed, and the first galaxy mergers happened, and the first supermassive black hole pairs began their slow, billion-year spirals toward each other in the cores of those merged galaxies. The hum was here before us, will be here after us. We did not create it. We did not change it by detecting it. We only, finally, noticed it. And the noticing required a chain of understanding so long and so intricate that it is worth tracing for just a moment. Einstein's general relativity in 1916, which predicted waves even their author doubted could be measured. Jocelyn Bell Burnell and her chart recorder paper in 1967, noticing a smudge of regular signal in the noise. Hulse and Taylor in 1974, catching a binary pulsar and watching its orbit decay for years, until the numbers told a story about energy leaking away as gravitational radiation. The engineers who built Arecibo and the Green Bank Telescope and Parkes and FAST and Meerkat and Effelsberg and the rest. The theorists who worked out the Hellings-Downs curve in 1983. Giving future observers a fingerprint to hunt for. The astronomers who began timing millisecond pulsars one by one, building a catalogue of dead star clocks across the galaxy. The graduate students and postdocs who ran the analysis pipelines through years of ordinary data that showed nothing obvious. The collaboration that kept going after one of its most important instruments fell into its own dish on a December morning in 2020. And then, in the last week of June 2023, the papers appeared. 4 collaborations. Multiple journals. One result. Something is humming. At roughly 3.5 sigma, we can say, it is there. The quadrupole correlation is present. The Hellings-Downs fingerprint has been found. We do not yet know with certainty what every part of it means. The spectrum may hide things. The exotic early universe sources may be whispering alongside the black holes. The final parsec problem may be resolved in ways that the current data cannot yet distinguish. But the hum is real. And the wave itself, the one causing this hum, the one whose pattern is written in the ticks and skipped ticks of 67 dead stars, that wave is passing through you, even now, as you drift toward sleep. You will never hear it. Nothing with ears could. It is cycling at a frequency so far below hearing that the gap between you and it is larger than the gap between the highest note a bat can register and the lowest note a whale sings. It exists in a domain of frequency so slow that your entire lifetime is a small fraction of one oscillation. But it is here. It has always been here. And now, for the first time in the age of the universe, a species on a small planet around an ordinary star on the edge of an ordinary galaxy looked out at 67 dead stellar corpses scattered across thousands of light years. Watched them tick for 15 years, measured the hesitation in their ticking to the billionth of a second, and felt the wave. That is the thing that is so hard to hold in one thought without it slipping loose. The scale of the source, billions of solar masses, millions of light years apart, orbital periods longer than human civilization, and the delicacy of the measurement, nanoseconds. Dead stars, a curve named for two researchers who worked it out in 1983 and waited 40 years to see it confirmed. The mismatch between those two scales is almost violent, something immeasurably enormous, detected by something almost absurdly precise. And the bridge between them is patience. 15 years of it, every few weeks. Point the dish, record the pulse, log the arrival time, move on. Wherever you are listening from tonight, whatever corner of the world, whatever hour of the night, you are resting inside the very instrument that made this detection possible. Not as a metaphor. The space-time you occupy is what the waves travel through. The distances between you and the pulsars are what the waves alter. You are not a bystander to the measurement. You are part of the medium. And somewhere far above you, in the radio sky that your eyes cannot see, the millisecond pulsars are still spinning. PSA B 1937 plus 21, first of its kind, 641 times a second ticking, PSA J 4374715, nearest and brightest, patient and steady. All the others, unnamed to most of us, their radio beams sweeping past Earth like lighthouses in a fog none of us can see. The telescopes are still pointed. The data is still being collected. The analysis will continue, and every month the picture sharpens a little more. More years, more pulsars, the square kilometre array coming online with its vastly greater sensitivity. The hum will resolve, slowly, into something more detailed. Individual voices may emerge from the crowd. The spectrum will grow clearer and tell us more precisely what is singing. And someday, in 10 years or 20 or 50, a new generation of researchers will sit down with data we cannot yet imagine and read from the gravitational wave background a record of events that no light can ever show us. The universe's first second, the moment of inflation, the cooling and the phase transitions and the settling of the laws of physics into the forms they hold today. Not because anyone builds an instrument to measure those things, but because the hum is already there, carrying all of it, washing through the galaxy continuously, and we are learning, slowly, how to listen. You do not need to grasp every number to feel the shape of what happened here. You do not need to hold the Hellings-Downs curve in your mind as you fall asleep, or remember the exact significance level, or recall the names of all 67 pulsars. What matters is this: for 100 years, since Einstein wrote the equations and then doubted his own result, humanity tried to feel the geometry of space-time move. And we did it. First with a chirp, fleeting and local, and then with a hum, ancient and universal. Two detections, each astonishing in its own way. Both real, both telling us that the universe is not silent and still. It is brimming with motion at every scale, from the millisecond merger of stellar mass black holes to the billion-year slow dance of the most massive objects in existence. You live inside all of it. The hum passes through you as you drift. The pulsars tick above. The black holes dance, impossibly far away, impossibly slowly, stirring the whole of space in their wake. And the little dishes on Earth, in the hills of Puerto Rico where Arecibo stood, in the quiet of West Virginia, in the Karoo Desert and the hills of Guizhou and the fields of England and the Nanay Plain in France, they keep watching, keep listening, keep recording the nanosecond hesitations of dead stars. There is something deeply comforting in that, I think. Not in any grand philosophical sense, just the simple fact of it. That people set out to feel something so faint and so vast, and they did not give up, and eventually the universe showed its hand. If you drifted off somewhere in all of that, that's perfectly all right. The hum will still be here when you wake. It was here before us, and it will outlast us, and it does not require our attention to continue. But if you are still with me, wherever you are in the night, whatever blanket you have pulled up, whatever lamp is still softly on, thank you for sitting with this one. It was a big one, a slow one, with a lot of patient waiting in it, which felt right for a story about 15 years of watching dead stars. If this is the kind of night you want more of, a quiet like or a subscribe keeps Grandpa's late nights going, and small channels like this one really do rely on your support to keep these slow journeys coming. Tell me where you are in the world tonight. What time is it in your corner of the dark? I love knowing where these words land. Until next time, sleep well, dream of spinning stars and slow black holes and the patient geometry of space. Good night, kiddo. Grandpa'll leave the porch light on.